There is a star visible to the naked eye, hanging in the southern sky that is tearing itself apart. Not slowly, not gently. It is losing mass equivalent to the entire Earth every few months, shredding its own body into space at speeds exceeding 6,000 kilometers per second. That is more than 2% of the speed of light. And it has been doing this for hundreds of thousands of years. It sits roughly 1,090 light years from where you are right now. Close enough to see without a telescope. Close enough to be one of the brighter points of light in the constellation Vela, the sails. Its name is Gamma Velorum, and it is the nearest and brightest Wolf-Rayet star system known to science. Most people have never heard of it. Most astronomers rarely mention it to the public. But what is happening inside that system, right now, at this very moment, is one of the most violent and consequential processes in the entire galaxy. Wolf-Rayet stars are not ordinary stars. They are the exposed, dying cores of the most massive stars in existence, stars that were born with 20, 40, even 80 times the mass of our Sun. They have burned through their fuel with reckless speed, and now their outer layers are being blasted into the void by radiation pressure so extreme that nothing can hold the star together. The surface temperature of the Wolf-Rayet star in the Gamma Velorum system exceeds 57,000 degrees Celsius. That is nearly 10 times hotter than the surface of our Sun. At that temperature, the star does not merely glow, it screams in ultraviolet light, invisible to our eyes but lethal to anything in its path. And the wind it produces, a torrent of ionized gas and stripped atoms, moves so fast that if you could stand on a planet near that star, the wind alone would strip the atmosphere from your world in a matter of hours. A wind moving at 6,000 kilometers per second does not blow past you, it erases you. But here is what makes Gamma Velorum truly extraordinary. It is not a single star. It is a binary system. Two massive stars locked in a gravitational dance, orbiting each other once every 78.5 days. One of those stars is the Wolf-Rayet component, an object so extreme that it has already shed more than half of its original mass. The other is a blue supergiant, an O-type star burning at 35,000 degrees, itself one of the hottest and most luminous types of star in the universe. Together, their combined luminosity is more than 200,000 times that of the Sun. 200,000 suns, compressed into a single point of light in the night sky. And where their stellar winds collide, in the space between them, temperatures reach tens of millions of degrees, producing X-rays that can be detected by orbiting telescopes from across the galaxy. The collision zone is a standing shockwave, a permanent region of superheated plasma between two dying giants. It is one of the most energetic phenomena known in stellar astrophysics, and it happens continuously, every second of every day, just over 1,000 light-years from Earth. And it gets stranger. The Wolf-Rayet star in this system is on borrowed time. It has perhaps a few 100,000 years left before it exhausts its remaining fuel. When it does, it will collapse. The core will implode in a fraction of a second, and the result will be a supernova, an explosion so bright it could briefly outshine every other star in the Milky Way. At 1,090 light-years away, Gamma Velorum is close enough that when that supernova occurs, it will be visible in broad daylight on Earth. It will cast shadows at night. The sky will change. And depending on the orientation of the explosion, depending on whether the star's rotational axis points toward us or away, there is a small but non-zero chance that the death of this star could produce a gamma-ray burst, a focused beam of energy so powerful that it could damage the ozone layer of our planet from over 1,000 light-years away. This is not a distant abstraction. This is not a theoretical exercise about some faint smudge in a telescope. This is a star you can see with your eyes tonight from the southern hemisphere, and it is dying. By the end of tonight, you're going to understand what Wolf-Rayet stars are, why they matter, and why Gamma Velorum, this beautiful, terrifying binary system in the constellation Vela, represents one of the most important objects in our galaxy for understanding how massive stars live, die, and reshape the universe around them. You will understand the physics of stellar winds that move at thousands of kilometers per second, the chemistry of dust forming in the shadows of colliding shockwaves, and the haunting question of what happens when a star this close to Earth finally reaches the end of its life. We will trace the history of its discovery, follow the light from its surface across 1,000 years of space, and confront the unsettling reality that the universe has placed one of its most dangerous objects in our celestial backyard. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand Gamma Velorum, we first need to understand what a star actually is, not in the abstract feel-good sense, in the physical, violent, thermodynamic sense. A star is a sphere of gas held together by its own gravity, heated to such extremes that the atoms in its core are crushed together, fusing lighter elements into heavier ones and releasing energy in the process. This is nuclear fusion, the same process that powers a hydrogen bomb, except a star does it continuously, for millions or billions of years, balancing the outward push of radiation against the inward pull of gravity. Our Sun does this quietly, steadily, converting about 4 million tons of matter into pure energy every single second. It has been doing this for 4.6 billion years and will continue for roughly another 5 billion. It is, by cosmic standards, a calm and unremarkable star, but our Sun is small. It sits near the middle of the stellar mass range, classified as a G-type main sequence star, sometimes called a yellow dwarf. Its surface temperature is about 5,500 degrees Celsius. Its luminosity, the total amount of energy it produces each second, is about 3.8 times 10 to the power of 26 watts. These are enormous numbers by human standards, but modest by stellar standards. The Milky Way contains roughly 200 to 400 billion stars, and many of them dwarf the Sun in every measurable way. The range of stellar masses spans nearly 3 orders of magnitude, from tiny red dwarfs at 1/10 of a solar mass to the most massive stars known, which can exceed 100 solar masses. And the consequences of that mass range are profound, because the mass of a star at birth determines almost everything about its life, its temperature, its luminosity, its lifespan, and above all, the manner of its death. Consider, for instance, a star born with 10 times the mass of the Sun. Such a star burns its fuel not tens faster, but thousands of times faster. The relationship between mass and luminosity in stars is not linear. It follows a power law, roughly proportional to the mass raised to the third or fourth power. A star with 10 solar masses might shine 10,000 times brighter than the Sun. A star with 50 solar masses might shine 1,000,000 times brighter. And this furious rate of energy production means that massive stars live dramatically shorter lives. While our Sun will endure for about 10 billion years, a star of 50 solar masses might exhaust its core hydrogen in just 3 to 4 million years. That is less than 1,000th of the Sun's lifetime. In cosmic terms, massive stars are born, burn with extraordinary brilliance, and die almost immediately. To put this in more tangible terms, imagine compressing the Sun's entire 10 billion year lifespan into a single human year. The Sun would be born on January 1st and would die of old age on December 31st. On that same timescale, a 50 solar mass star would be born on January 1st and would be dead before sunrise on January 2nd. Its entire existence, from the moment of ignition to the final supernova, would occupy less than 1 day out of 365. And during that single day, it would produce more light and heat than the Sun generates in its entire year-long life. Massive stars do not simply live fast and die young. They live violently and die catastrophically. They are the mayflies of the stellar world, burning through their inheritance in a blaze that can be seen across the galaxy. Now, scale that understanding upward. The Wolf-Rayet star in the Gamma Velorum system, known formally as WR11, was not born with 10 or 20 solar masses. It was born with at least 35 to 40 solar masses, possibly more. During its main sequence lifetime, when it was still fusing hydrogen in its core, it would have been one of the brightest and most massive stars in its region of the galaxy. Its surface temperature would have exceeded 40,000 degrees Celsius. Its luminosity would have been hundreds of thousands of times greater than the Sun. If you could have replaced our Sun with that star at the moment of its birth, the Earth would not have existed. The radiation alone would have vaporized every rocky body within several astronomical units. Mercury, Venus, Earth, Mars, all would have been reduced to expanding clouds of ionized gas within the first few thousand years. The habitable zone, the region where liquid water could exist on a planetary surface, would have been pushed out beyond the orbit of Neptune. Here is a way to grasp the scale. If you shrank the Sun down to the size of a basketball, then the Earth would be roughly the size of a small peppercorn, sitting about 26 meters away. At that same scale, the young star that would become WR11 would not be a basketball. It would be closer to the size of a large beach ball, perhaps 60 centimeters across, and it would glow so fiercely that you could not look at it from across a football field without damaging your eyes. Now imagine that beach ball not just glowing, but actively throwing off material, shedding its outer layers like a dandelion in a hurricane, sending streams of plasma outward in every direction at thousands of kilometers per second. That is what a Wolf-Rayet star does. It destroys itself with its own light. To grasp just how fast these winds move, consider the following comparison. A commercial jetliner cruises at roughly 900 kilometers per hour. A bullet from a high-powered rifle travels at about 3,000 kilometers per hour. The fastest human-made object ever launched, the Parker Solar Probe, at its closest approach to the Sun, reaches speeds of about 690,000 kilometers per hour. The wind from the Wolf-Rayet star in Gamma Velorum moves at approximately 5.4 million kilometers per hour. That is nearly 8 times faster than the fastest spacecraft humanity has ever built. And it is not a brief burst. It is a continuous outflow, a permanent gale of ionized matter pouring from the star's surface in every direction, day and night, century after century, carrying away mass at a rate that would drain an entire ocean in seconds. If you could somehow stand in the path of that wind and survive the temperature, the pressure alone would be equivalent to being hit by millions of tons of material per square meter every second. The wind does not blow past you, it erases you. The concept of a Wolf-Rayet star was first identified in 1867 when 2 French astronomers at the Paris Observatory, Charles Wolf and Georges Rayet, noticed something peculiar. They were conducting spectroscopic surveys of stars in the constellation Cygnus, the Swan, breaking starlight into its component wavelengths to study the chemical composition of stellar atmospheres. Spectroscopy, the science of splitting light into a rainbow and reading the dark and bright lines within it, was still a relatively new tool in astronomy at that time. Gustav Kirchhoff and Robert Bunsen had only established the fundamental laws of spectroscopy in 1859 and 1860, showing that each chemical element produces a unique pattern of spectral lines, like a fingerprint. By 1867, astronomers were eagerly applying this technique to stars, classifying them by the patterns in their spectra. Most stars produce absorption spectra, patterns of dark lines, where specific elements in the star's atmosphere absorb light at characteristic wavelengths, leaving gaps in the rainbow. But 3 stars in Wolf and Rayet's survey showed the opposite. Instead of dark absorption lines, these stars displayed bright emission lines, broad and intense, unlike anything the 2 astronomers had seen before. The lines indicated the presence of helium, nitrogen, and carbon, but they were so broadened, smeared out across a wide range of wavelengths, that the gas producing them had to be moving at extraordinary speeds. Something was blasting material off these stars at velocities that no one in the 1860s could explain. The 3 stars they identified that night, now catalogued in modern databases, became the founding members of the Wolf-Rayet class. For decades, these objects remained mysterious. More Wolf-Rayet stars were gradually discovered, mostly by spectroscopic surveys in the early 20th century. But their nature was unclear. Were they young stars still forming? Were they old stars in some exotic state? Were they binary systems where material was being transferred between 2 stars? Different astronomers proposed different explanations, and the debate continued for nearly a century. Carlisle Beals, a Canadian astronomer working at the Dominion Astrophysical Observatory in Victoria, British Columbia, made important contributions in the 1920s and 30s by carefully measuring the velocities implied by the broad emission lines. He demonstrated that the emission came from gas moving outward from the star at speeds of 1,000 to 3,000 kilometers per second, and he proposed that Wolf-Rayet stars were surrounded by rapidly expanding envelopes of gas, continuously replenished from the stellar surface. This was an early version of what we now call a stellar wind, though the physical mechanism driving it was not yet understood. The breakthrough came in the 1960s and 70s, when computing power became sufficient to simulate the internal structure and evolution of massive stars. Bogdan Paczynski, a Polish-American astronomer working at the Nicolaus Copernicus University, and later at Princeton, published a landmark paper in 1967 proposing that Wolf-Rayet stars were the exposed helium-burning cores of massive stars that had lost their hydrogen envelopes. His models showed that a star born with sufficient mass could lose its outer layers through a combination of stellar, winds, and in binary systems, mass transfer to a companion star, eventually revealing the hot, dense core beneath. This idea was revolutionary because it placed Wolf-Rayet stars not at the beginning of stellar life, but near its end, the penultimate stage before a massive star dies in a supernova. Subsequent work by Peter Conti at the University of Colorado, who in 1976 proposed the Conti scenario for massive star evolution, and by André Mader and Georges Ménet at the Geneva Observatory, who incorporated the effects of mass loss and rotation into detailed evolutionary models, refined and solidified this picture over the following decades. Here is what happens, as we now understand it. A star born with more than about 25 solar masses spends a few million years on the main sequence, fusing hydrogen into helium through the carbon-nitrogen-oxygen cycle. When the hydrogen in its core runs out, it begins fusing helium, then carbon, then neon, then oxygen, then silicon, building up heavier and heavier elements in concentric shells around an ever denser core. But long before this process is complete, the star's enormous luminosity begins to drive powerful stellar winds. The mechanism is radiation pressure acting on spectral lines, a process first worked out in detail by Leon Lucy and Philip Solomon in 1970, and subsequently developed into a comprehensive theory by John Castor, David Abbott, and Richard Klein in 1975, in what became known as the cake theory. Photons from the star's interior are absorbed by ions in the outer atmosphere, transferring their momentum to the gas and accelerating it outward. In massive luminous stars, this process is extraordinarily efficient because the sheer number of photons is so vast that even a small fraction being absorbed can drive a powerful wind. These winds carry mass away from the star at rates that can exceed 10 to the negative fifth solar masses per year. That might sound small. It is not. It is roughly one solar mass every 100,000 years, or approximately one Earth mass every 60 days. Over hundreds of thousands of years, a star can lose more than half its original mass to these winds, an outpouring of material that enriches the surrounding space with processed nuclear material. The outer hydrogen envelope is stripped away entirely, first exposing nitrogen-enriched material from the hydrogen-burning shell, which produces a WN-type Wolf-Rayet spectrum, and then, as stripping continues, exposing the carbon and oxygen-enriched products of helium burning, creating a WC-type spectrum. The rarest subtype WO shows oxygen emission lines and indicates stripping down nearly to the carbon-oxygen core itself. Each subtype represents a progressively more advanced stage of self-destruction. The Wolf-Rayet star in Gamma Velorum is classified as WC8, meaning it is a carbon-rich Wolf-Rayet star, deep into the process of exposing its helium-burning interior. It has already passed through the WN phase, already shed its nitrogen-enriched layers, and now reveals the products of helium burning at its surface. In the evolutionary sequence of massive star death, it is approaching the final chapters. To put this timeline in perspective, consider the full sweep of human time against the cosmic clock. The Sun has existed for 4.6 billion years. Human civilization, in its earliest forms, has existed for perhaps 10,000 years. The entire recorded history of astronomy spans about 5,000 years. The Wolf-Rayet phase of a massive star's life lasts perhaps 200,000 to 500,000 years. That sounds like a long time, but compared to the star's total lifetime of a few million years, it is the final fraction of a percent. If the entire life of a massive star were compressed into a single calendar year, the Wolf-Rayet phase would begin sometime in the last week of December. The supernova that follows would occur in the final second before midnight on December 31st. We are watching Gamma Velorum in its final days, cosmically speaking. The fact that we happen to exist during this brief window, the fact that we have developed the tools to study it during this fleeting moment, is itself a remarkable coincidence, though one that is made less surprising by the realization that Wolf-Rayet stars, while rare individually, are common enough that at any given time, the Milky Way contains roughly 1,000 to 2,000 of them. The Gamma Velorum system was recognized as something unusual long before its Wolf-Rayet nature was confirmed. The star has been known since antiquity. Arab astronomers catalogued it. European navigators used it. It is the brightest star in the constellation Vela, and was originally part of the much larger ancient constellation Argo Navis, the ship Argo, representing the mythological vessel sailed by Jason and the Argonauts. Argo Navis was one of the original 48 constellations listed by Ptolemy in the 2nd century, and it remained a single constellation for nearly 2 millennia before the French astronomer Nicolas Louis de Lacaille, during his survey of the southern skies from the Cape of Good Hope in the 1750s, divided it into 3 smaller, more manageable constellations: Vela the sails, Puppis the stern, and Carina the keel, with an apparent visual magnitude of about 1.78. Gamma Velorum is easily visible to the naked eye from the southern hemisphere and from low northern latitudes. It appears as a single bright point of light, slightly bluish-white, indistinguishable from any other bright star to the untrained eye. But that appearance is deceptive in almost every way that matters. The light reaching your eye from Gamma Velorum has been travelling for roughly 1,090 years. It left the system around the time of the Norman conquest of England, around the founding of the Song dynasty in China, around the period when Leif Erikson was exploring the coast of North America. The photons that strike your retina tonight were emitted when the medieval world was taking shape, and they carry within their wavelengths a record of conditions so extreme that no laboratory on Earth can reproduce them. The bluish-white colour, barely perceptible to the naked eye, is a clue. It tells you that the light source is hot, much hotter than the sun, which appears yellowish-white. But the true nature of that heat only becomes apparent when you spread the light into its component wavelengths, when you pass it through a prism or a diffraction grating and examine the resulting spectrum. And it was through spectroscopy that the extraordinary nature of Gamma Velorum was first revealed. The spectroscopic story begins in the second half of the 19th century, during the golden age of astronomical spectroscopy, when astronomers across Europe were systematically cataloguing the spectra of bright stars. Most stellar spectra show dark absorption lines, narrow dips in brightness at specific wavelengths corresponding to the absorption of light by atoms in the star's outer atmosphere. These absorption lines formed the basis of the spectral classification system developed by Annie Jump Cannon at Harvard, the familiar sequence of O, B, A, F, G, K, M that sorts stars by surface temperature. But a handful of stars refused to fit this scheme. Instead of absorption lines, they showed broad, bright emission lines, peaks in the spectrum rather than dips, indicating that these stars were surrounded by extended atmospheres of hot, glowing gas that was emitting light rather than absorbing it. The first such star was observed by Charles Wolfe and Georges Rayet at the Paris Observatory in 1867, using the 40-centimetre refractor at the observatory station in Montrouge. They identified 3 faint stars in the constellation Cygnus, whose spectra showed broad, intense emission bands, unlike anything seen in normal stellar spectra. The class of stars they had identified would eventually bear their names Wolf-Rayet stars, though the physical explanation for their peculiar spectra would not come for another century. Gamma Velorum was recognized as a member of this class relatively early. Its emission line spectrum was noted by several observers in the late 19th and early 20th centuries, and it quickly became the brightest and most accessible example of the Wolf-Rayet phenomenon. The emission lines in its spectrum are extraordinary. They are enormously broad, spanning tens of angstroms in wavelength, indicating that the emitting gas is moving at velocities of thousands of kilometers per second. They are also complex in profile, showing flat tops, rounded peaks, and asymmetric wings that encode information about the geometry and velocity structure of the outflowing wind. The dominant emission lines in the spectrum of Gamma Valorum's Wolf-Rayet component come from highly ionized carbon and helium, the signature elements of a WC-type Wolf-Rayet star. Carbon-3, Carbon-4, Helium-1, and Helium-2 lines dominate the optical spectrum, creating a pattern of broad, overlapping emission features that make the spectrum look utterly unlike that of any ordinary star. To an astronomer trained in normal stellar spectroscopy, the spectrum of a Wolf-Rayet star looks wrong, almost alien, a chaotic jumble of emission where there should be orderly absorption. It took decades of theoretical work to understand that this apparent disorder actually encodes a precise physical message about a star in the act of destroying itself. But even small telescopes reveal that it is not a single star. It is a visual double, and further observation reveals it to be a complex multiple star system containing at least 6 components arranged in a hierarchical architecture. The outermost companions are faint and widely separated, likely gravitationally bound, but orbiting at enormous distances, with periods measured in thousands or millions of years. The 2 brightest components, designated Gamma-2 Velorum A and Gamma-2 Velorum B, form the close binary pair that contains the Wolf-Rayet star and its O-type companion. This close pair is the heart of the system, the engine that produces the violent wind collision phenomena that make Gamma Velorum one of the most studied stellar systems in the southern hemisphere. The binary nature of the central pair was confirmed through spectroscopic observations beginning in the early 20th century. By analyzing the periodic Doppler shifts in the spectral lines of both stars, astronomers determined that the 2 components orbit each other with a period of 78.53 days. The orbit is mildly eccentric, meaning it is not perfectly circular but slightly elliptical, with an eccentricity of about 0.33. At their closest approach, known as periastron, the 2 stars are separated by roughly 0.6 astronomical units, less than the distance between our Sun and Venus. At their farthest separation, known as apastron, they are about 1.2 astronomical units apart, roughly the distance from the Sun to the Earth's orbit. 2 enormous, luminous, dying stars, one of them actively shredding itself to pieces, orbiting each other at a distance comparable to the inner solar system. Imagine standing on a hypothetical planet at the orbit of Jupiter. In place of our quiet yellow sun, you would see 2 brilliant blue-white objects, one slightly dimmer and surrounded by a glowing halo of expelled material, circling each other every 2.5 months. The sky would never be truly dark. The radiation would be lethal. The gravitational and radiative interactions between these 2 stars create phenomena that cannot be observed anywhere else in our cosmic neighborhood. But here is the problem. Despite being relatively close to us, despite being visible to the naked eye, despite being studied for over a century, Gamma Velorum remains one of the most difficult stellar systems to model accurately. The Wolf-Rayet component is surrounded by such a thick, fast-moving stellar wind that its true surface, if it even has a well-defined surface, is obscured. Unlike the Sun, which has a clearly defined photosphere, where the gas transitions from opaque to transparent, the Wolf-Rayet star's surface is buried beneath layers of outflowing gas that extend for many stellar radii. The optical depth, the measure of how opaque the wind is to light, remains greater than 1 out to several stellar radii, meaning that the effective surface of the star, the layer from which we receive most of the light, is actually the wind itself, not the underlying hydrostatic core. The radius you measure depends on the wavelength you observe at, because different wavelengths probe different depths in the wind. In the infrared, where the wind is more transparent, the star appears smaller. In the ultraviolet, where the wind is more opaque, the star appears larger. There is no single, well-defined surface. The star blends into its own wind, becoming more atmosphere than object. The mass loss rate, the chemical composition, the internal structure, all of these fundamental properties must be inferred indirectly through spectroscopic modeling, X-ray analysis, and polarimetric observation. Different research groups have published different values for the star's mass, luminosity, and evolutionary state, sometimes disagreeing by factors of 2 or more. And the question that drives much of this research, the question that makes Gamma Velorum not just scientifically interesting but genuinely important, is simple. How will this star die? When the Wolf-Rayet component finally collapses, will it produce a normal core collapse supernova? Will it produce a hypernova? Could it produce a gamma-ray burst? And what will the consequences be for the surrounding interstellar medium, for the nearby star-forming regions, and for any planetary systems that might exist within a few hundred light years? Then something happened that changed everything. When astronomers turned the most powerful X-ray telescopes in history toward the space between these two stars, they found a collision more violent, more complex, and more consequential than any model had predicted. The first serious attempt to understand the physics of the Gamma Velorum binary system came in the 1970s and 80s, when X-ray astronomy was still a young field. Orbiting X-ray observatories, beginning with the Uhuru satellite launched in 1970 and continuing through the Einstein Observatory launched in 1978, had revealed that many hot stars produced X-rays, but not always in the amounts or patterns that simple models predicted. Single O-type stars, for instance, were expected to produce soft X-rays from shocks embedded in their stellar winds, small-scale collisions within the turbulent outflow itself, and they did. But binary systems containing two massive stars with powerful winds showed something different. Their X-ray emission was harder, meaning the individual photons carried more energy. The emission was also variable, changing in intensity as the two stars orbited each other, sometimes by factors of 2 or more over the course of a single orbit. And in some cases, the X-ray luminosity was far greater than the sum of what each star would produce individually. Something in the interaction between the two winds was creating temperatures and energies far beyond what either star could generate alone. The theoretical framework for understanding this was developed in the 1970s and refined throughout the 80s and 90s by researchers including Ian Stevens, Julian Pittard, and others at the University of Birmingham and later at the University of Leeds. When two stars in a binary system both produce powerful stellar winds, those winds expand outward from each star and inevitably collide in the space between them, creating a region known as the Wind Collision Zone, or WCZ. At the boundary where the two winds meet, the kinetic energy of the flowing gas is converted into thermal energy through shock heating. The physics is conceptually simple, though mathematically challenging. Two streams of gas, each moving at thousands of kilometers per second, slam into each other and stop. The kinetic energy has to go somewhere, and it goes into heat. The temperature in the resulting shocked region can reach tens of millions of degrees, hot enough to strip electrons from the inner shells of heavy atoms and to emit copious amounts of X-ray radiation. The geometry of the collision zone depends on the relative strengths of the two winds, specifically on the ratio of their momentum fluxes, which is the product of the mass loss rate and the wind velocity for each star. If one star has a much stronger wind than the other, the collision zone wraps around the weaker wind star like a bow shock, similar to the bow shock that forms when the solar wind encounters the magnetic field of Earth. If the winds are of comparable strength, the collision zone forms a relatively flat surface between the two stars, like a wall of superheated gas dividing the space between them. In the case of Gamma Velorum, the Wolf-Rayet star has the dominant wind, with a mass loss rate roughly 100 times greater than that of its O-type companion. Though the O-type star's wind is faster, the collision zone therefore wraps around the O-type star, forming a cone-shaped shock structure that opens away from the Wolf-Rayet component. The opening angle of this cone depends on the exact momentum ratio and has been estimated at roughly 40 to 60 degrees from the axis connecting the two stars. This wind collision zone in Gamma Velorum has been studied by nearly every major X-ray observatory of the modern era. The Rosetta satellite, a joint German-American-British mission launched in 1990, observed it in the early 1990s and confirmed the presence of soft X-ray emission consistent with hot shocked plasma. The Japanese-American ASCA satellite, launched in 1993, provided improved spectral resolution and began to reveal the temperature structure of the emitting region. But the true revolution came with the launch of two next-generation X-ray observatories in 1999, the Chandra X-ray Observatory, built by NASA and named after the Nobel Prize-winning astrophysicist Subramanian Chandrasekhar, and XMM Newton, built by the European Space Agency. These two telescopes, still operating more than 25 years later, provided unprecedented angular resolution and spectral sensitivity, allowing astronomers to study the X-ray emission from Gamma Velorum in exquisite detail. What they found confirmed the theoretical predictions in some ways, but challenged them in others. The X-ray emission from Gamma Velorum is indeed variable, with the orbital period of 78.53 days, reaching a minimum when the Wolf-Rayet star is between the observer and the O-type star, a configuration in which the dense Wolf-Rayet wind lies along the line of sight to the collision zone, absorbing some of the X-rays before they can reach our telescopes. The emission reaches a maximum when the O-type star is in front, and the collision zone is most directly visible, with the least amount of absorbing material in the way. This orbital modulation of the X-ray flux was exactly what the colliding wind models predicted, and its detection was a strong confirmation of the basic theoretical picture. But the total X-ray luminosity was lower than early models had predicted, roughly 10 to the 32 to 10 to the 33 ergs per second, depending on the orbital phase and the energy band considered. This is a factor of several to 10 below the predictions of simple adiabatic shock models, which assume that all of the kinetic energy in the colliding winds is converted into heat and then radiated away as X-rays. Something was suppressing the X-ray output. Some of the kinetic energy was being diverted into other channels. The discrepancy was not small enough to attribute to measurement uncertainty. It demanded an explanation. Several explanations were proposed. The first was radiative cooling. In the densest parts of the wind collision zone, particularly near the stagnation point where the two winds first collide head-on, the gas density is high enough that the cooling time, the time for the shocked gas to radiate away its thermal energy, is shorter than the flow time, the time for the gas to move away from the shock and escape downstream. When cooling is efficient, the shocked gas does not stay at tens of millions of degrees. It cools rapidly, emitting its energy at lower temperatures in the form of ultraviolet and optical photons, rather than X-rays. This process, known as radiative braking or radiative cooling of the shock, effectively converts would-be X-ray emission into lower energy radiation that is harder to detect and easier to confuse with other sources of light in the system. Detailed hydrodynamic simulations by Julian Pittard and others showed that radiative cooling can indeed reduce the X-ray luminosity of a colliding wind binary by significant factors, particularly in systems where the winds are dense and the orbital separation is small. The second explanation involved particle acceleration. In the late 1990s and early 2000s, astronomers began to detect non-thermal radio emission from several colliding wind binary systems. Non-thermal emission, in this context, refers to radiation produced by electrons moving at close to the speed of light, spiraling around magnetic field lines and emitting synchrotron radiation, a characteristic form of electromagnetic emission produced by relativistic charged particles in magnetic fields. The presence of synchrotron radiation meant that the wind collision zone was acting as a natural particle accelerator, taking electrons from the stellar winds and boosting them to relativistic energies through a process known as diffusive shock acceleration, sometimes called first-order Fermi acceleration. This is the same mechanism believed to operate in supernova remnants and to be responsible for producing cosmic rays, the high-energy particles that pervade the galaxy and constantly bombard Earth's atmosphere. If a significant fraction of the kinetic energy in the colliding winds is channeled into accelerating particles rather than heating gas, that energy would not appear as thermal X-ray emission, explaining the deficit. Gamma Velorum, in other words, is not just a binary star system. It is a cosmic accelerator producing high-energy particles in the space between its two stellar components. And this discovery connected it to a much larger question in astrophysics, the origin of cosmic rays. the mystery of how particles in the galaxy are accelerated to energies millions of times greater than anything achievable in a human-built particle accelerator. But here is the problem. The detection of non-thermal radio emission from Gamma Velorum specifically proved to be elusive and inconsistent. While several other colliding wind binaries, such as WR140 in the constellation Cygnus and WR147 in the same region, showed clear and persistent non-thermal radio signatures, Gamma Velorum's non-thermal emission was weaker and more difficult to separate from the thermal free emission of its dense stellar winds. Free emission, also known as Bremsstrahlung, is the radiation produced by free electrons being deflected by the electric fields of ions, and it is the dominant form of radio emission from the ionized stellar winds of hot stars. The spectrum of free emission has a characteristic dependence on frequency that differs from the spectrum of synchrotron emission, so in principle the two can be separated. But in practice, when the thermal emission is strong and the non-thermal emission is weak, the separation requires very precise measurements across a wide range of radio frequencies. The Wolf-Rayet wind in Gamma Velorum is so thick, so opaque to radio waves, that any non-thermal emission generated deep in the collision zone must fight through a wall of absorbing material before it can reach our telescopes. Observations at different radio frequencies and at different orbital phases yielded conflicting results. Some studies claimed detections, others set upper limits that were uncomfortably close to the claimed detections. The question of whether Gamma Velorum is indeed a significant particle accelerator remained, for many years, frustratingly unresolved. Understanding the mass loss rate of the Wolf-Rayet star is central to almost every aspect of this system's physics, and it is here that one of the deepest and most persistent controversies in Wolf-Rayet astrophysics has played out. The traditional method for measuring a Wolf-Rayet star's mass loss rate is to analyze its emission line spectrum. The strength of emission lines, particularly those of helium and carbon, depends on the density of the wind, which in turn depends on how much mass the star is losing per unit time. The relationship is well established by atomic physics. More dense wind means more atoms per unit volume, which means more collisions between atoms and electrons, which means stronger emission lines. Early analyses of Gamma Velorum's spectrum, conducted in the 1980s and 90s by teams using codes such as those developed by John Hillier and by Wolf Rainer Hamann, yielded mass loss rates of roughly 5 times 10 to the negative 5th solar masses per year. That is approximately 1 solar mass every 20,000 years, or roughly 1 Earth mass every 2 months. These rates were consistent with theoretical predictions for a WC8 star and were used as inputs for all subsequent modeling of the system, from X-ray emission to wind dynamics to dust formation. But in the late 1990s, a troubling discrepancy began to emerge. Theoretical work on stellar winds, particularly by Stanner Waukee at the University of Delaware, David Cohen at Swarthmore College, and their collaborators showed that Wolf-Rayet winds are not smooth, homogeneous outflows as had been assumed in virtually all previous analyses. Instead, they are clumpy, fragmented into dense knots and filaments separated by regions of much lower density, like a fog broken into patches by wind. The physical origin of this clumping is the line-driving instability, a fundamental instability in the radiation-driven acceleration mechanism that powers these winds. The instability was first identified in theoretical work by Lucian White in 1980, and subsequently studied in detailed numerical simulations by Stanner Waukee, Stan Pauls, and others. Small perturbations in the wind's velocity grow rapidly as the radiation field interacts with the moving gas, creating shocks and compressions that fragment the outflow into a complex, turbulent structure. The clumps are denser than the average wind, and the spaces between them are much more tenuous, and the consequence for mass loss rate determinations is devastating. Emission line strengths depend on the density squared, not the density itself, because the emission process involves two-body interactions between electrons and ions. This means that a clumpy wind with the same average mass loss rate as a smooth wind will produce stronger emission lines, because the denser clumps contribute disproportionately to the emission. Conversely, if you measure strong emission lines and assume a smooth wind, you will overestimate the mass loss rate. The clumps are boosting the signal, and if you do not account for them, you think the wind is denser and more massive than it actually is. When clumping was properly accounted for in the spectroscopic models, using volume filling factors that describe the fraction of the wind occupied by clumps, the revised mass loss rates came out 2 to 4 times lower than the original smooth wind estimates. The factor of reduction depends on the assumed clumping factor, which is itself uncertain and may vary with distance from the star. For Gamma Velorum specifically, this meant that the Wolf-Rayet star might not be losing mass at 5 times 10 to the negative fifth solar masses per year, as previously believed, but perhaps at only 1 to 2 times 10 to the negative fifth solar masses per year. This revision had cascading consequences that rippled through every aspect of the system's physics. Lower mass loss rates meant less momentum in the stellar wind, which affected models of the wind collision zone, changing the predicted geometry, temperature, and X-ray luminosity of the shock region. They meant less total mass lost over the star's Wolf-Rayet lifetime, which affected estimates of the star's current mass and thus predictions for its eventual supernova. A star that has lost less mass through its wind arrives at the pre-supernova stage with more mass remaining, which changes the dynamics of the core collapse and the properties of the resulting compact remnant. Lower mass loss rates even affected interpretations of the X-ray emission, since the absorbing column of wind material between the collision zone and the observer was now thought to be less dense than assumed, which changed the inferred intrinsic X-ray luminosity. And it gets worse. The distance to Gamma Velorum was itself uncertain for decades, and distance is fundamental to almost every derived quantity in astronomy. Luminosities, mass loss rates, physical separations, all depend on knowing how far away the system is, because the apparent brightness of an object decreases with the square of its distance. A star that appears to have a certain luminosity at a distance of 800 light-years has a very different luminosity if it is actually at 1,100 light-years. Ground-based parallax measurements, which determine distance by measuring the apparent shift of a star against the background of more distant stars as the Earth orbits the Sun, placed Gamma Velorum at various distances between roughly 800 and 1,400 light-years, with large error bars that reflected the difficulty of making such measurements from beneath the turbulent blanket of Earth's atmosphere. The Hipparcos satellite, launched in 1989 by the European Space Agency, was supposed to resolve this uncertainty with precise parallax measurements from space, above the atmosphere, free from the distortions that plague ground-based astrometry. Its catalogue, published in 1997 after years of data processing, gave a distance of roughly 840 light-years for Gamma Velorum, significantly closer than many previous estimates. This closer distance implied lower luminosities and lower mass loss rates, which in turn implied lower current masses for both stars. Some researchers embraced the Hipparcos distance and revised their models accordingly. Others argued that it was unreliable for such a bright, extended system, pointing out that the Hipparcos parallax solution for Gamma Velorum had unusually large residuals, statistical indicators that the measurement did not fit the data well, suggesting systematic errors in the analysis. The issue was not fully resolved until the Gaia satellite, launched in 2013 by the European Space Agency as the successor to Hipparcos, provided even more precise astrometric data. Gaia's second data release in 2018 and its subsequent releases confirmed a distance to the Gamma Velorum system of approximately 1,090 light-years, or about 335 parsecs. This was significantly farther than the Hipparcos value, vindicating those who had argued against the closer distance. The revised distance meant higher luminosities, higher mass loss rates, and higher current masses for both stars, bringing the system parameters back into better agreement with theoretical expectations for a WC8+0 type binary. But it also meant that more than a decade of published analyses based on the Hipparcos distance needed to be re-evaluated. Papers had been written, models had been built, conclusions had been drawn, all based on a distance that turned out to be wrong by roughly 30%. The lesson was sobering. In astronomy, Even the most fundamental measurements can carry systematic errors that persist for years and propagate through entire fields of research. The distance revision also forced astronomers to revisit the orbital dynamics of the system with fresh eyes. The masses of the two stars, determined from their orbital motion through Newton's laws of gravity, depend on the orbital inclination, the angle between the orbital plane and our line of sight. Spectroscopic observations alone cannot determine the inclination. They measure only the component of velocity along the line of sight, not the full three-dimensional motion. An orbit viewed face-on produces no measurable Doppler shifts at all, while an orbit viewed edge-on produces the maximum shifts. To determine the true masses, astronomers needed an independent measurement of the inclination, and this came from a technique called polarimetry. The light from gamma velorum is slightly polarized, meaning the electromagnetic waves oscillate preferentially in certain directions rather than randomly. This polarization arises because the free electrons in the stellar winds scatter light, and the asymmetric geometry of the binary system, with its wind collision zone and tidally distorted winds, means that the scattering is not perfectly symmetric. As the binary orbits, the geometry changes, and the polarization varies with a period matching the orbital period. By analyzing the pattern of polarization variation, astronomers can determine the orbital inclination and thus derive the true masses of both stars. Polarimetric studies of gamma velorum, particularly those by Robert St. Louis at the Université de Montréal and by Tony Moffat and colleagues, have yielded inclination estimates of roughly 65 to 70 degrees, indicating that we view the system at a moderately high angle, not quite edge-on but far from face-on. Combined with the spectroscopic orbital solution and the revised Gaia distance, this gives dynamical masses of approximately 9 solar masses for the Wolf-Rayet star and approximately 29 solar masses for the O-type companion. These values are among the most secure mass determinations for any Wolf-Rayet binary, and yet they still carry uncertainties of roughly 15 to 20%, reflecting the challenges of measuring polarimetric variations in a system where the intrinsic polarization is small and where the contributions of wind scattering, interstellar polarization, and instrumental effects must all be carefully disentangled. Let us take a moment to appreciate the physical environment inside this system as we now understand it. The Wolf-Rayet star, WR11, has a current mass estimated at roughly 9 solar masses, down from an original birth mass of perhaps 35 to 40 solar masses. It has lost more than 3/4 of its original substance to its relentless stellar wind, and possibly to mass transfer to its companion. What remains is essentially a bare stellar core, a ball of helium, carbon, and oxygen burning at temperatures exceeding 100 million degrees in its center. Its surface, to the extent that it has one, sits at roughly 57,000 degrees Celsius, emitting most of its light in the far ultraviolet, at wavelengths too short for the human eye to see. Its luminosity is approximately 170,000 times that of the Sun. Its wind is launched from near the stellar surface and accelerates outward, reaching terminal velocities of about 1,500 kilometers per second. The wind carries with it atoms of helium, carbon, and oxygen, along with trace amounts of heavier elements, all ionized to high-charge states by the intense ultraviolet radiation field that permeates the inner wind. The companion star, the O-type component, has a mass of roughly 29 solar masses and a surface temperature of about 35,000 degrees. It is itself a luminous and powerful star, producing a stellar wind with a terminal velocity of about 2,500 kilometers per second, faster than the Wolf-Rayet wind but much less dense. Its mass loss rate is roughly 100 times lower than that of its companion, but its wind still carries significant momentum. When these two winds collide in the space between the stars, they do so at a combined velocity that can exceed 3,000 kilometers per second. The kinetic energy in this collision is staggering. The wind collision zone produces enough energy to heat the shocked gas to temperatures of 40 to 50 million degrees, hot enough to emit X-ray photons that can be detected by satellites orbiting Earth over 1,000 light-years away. The collision zone extends roughly along the line connecting the two stars, curving around the O-type star and trailing downstream into a spiral pattern shaped by the orbital motion of the binary. Something is wrong with our assumptions about how these stars evolve. The traditional picture, the single-star evolutionary sequence from main sequence O star to luminous blue variable to Wolf-Rayet star to supernova, is clean and elegant, but it has been challenged repeatedly by observations that refuse to fit the model. Gamma Velorum is a case study in this tension. The current mass of the Wolf-Rayet component, roughly 9 solar masses, seems too low for a star that was born with 35 to 40 solar masses and is expected to produce a core collapse supernova at the end of its life. The standard models for single-star evolution would require extreme mass loss rates sustained over very long periods to strip the star down to this mass, but the revised, clumping-corrected mass loss rates are not high enough. The numbers do not add up. Something else must have contributed to the mass loss. The leading explanation is binary interaction. In a close binary system like Gamma Velorum, the two stars can exchange mass through a process called Roche-Lobe overflow. As one star expands during its post-main sequence evolution, it may fill its Roche-Lobe, the teardrop-shaped gravitational boundary, beyond which material is more attracted to the companion star than to the primary. When this happens, mass streams from the expanding star onto the companion, dramatically altering the evolutionary trajectories of both stars. The mass transfer can be stable or unstable, depending on the mass ratio and the evolutionary state of the donor star. In some cases, unstable mass transfer leads to a common envelope phase, where both stars orbit inside a shared envelope of gas, losing energy through friction and spiraling closer together. For Gamma Velorum, the Wolf-Rayet star may have lost a significant fraction of its mass, not through stellar winds alone, but through mass transfer to its O-type companion during an earlier evolutionary phase. This would explain how the star reached its current low mass without requiring unrealistically high wind mass loss rates. It would also explain the relatively high mass of the O-type companion, which at 29 solar masses is itself quite massive and may have gained some of that mass from its partner. But here's what makes this truly terrifying. If the Wolf-Rayet star in Gamma Velorum has indeed been stripped down to roughly 9 solar masses, it is approaching a critical threshold in stellar physics. The minimum mass required for a star to undergo core collapse and produce a supernova is roughly 8 solar masses. Below this threshold, a star will end its life as a white dwarf, shedding its outer layers gently through a planetary nebula phase and fading into a quiet, dense remnant. Above this threshold, the core grows too massive to support itself against gravity when nuclear fuel runs out, and it collapses catastrophically, triggering the supernova explosion. At 9 solar masses, the Wolf-Rayet star in Gamma Velorum is right at the edge. Its fate may depend on details we do not yet understand, details of its internal structure, its rotation rate, its magnetic field, the exact sequence and timing of nuclear burning in its core, and the amount of additional mass it will lose through its wind before the final collapse. But most models agree that it will indeed collapse, and when it does, the explosion will be one of the closest supernovae to Earth in the recorded history of our species. The question of what happens when the Wolf-Rayet star in Gamma Velorum dies has driven decades of research across multiple subfields of astrophysics. It is not a simple question. The outcome depends on a web of interconnected variables, each uncertain, each influencing the others, and each carrying implications that reach far beyond a single star system. Let us walk through the major angles from which astronomers have approached this problem, one by one, and see what each reveals and where each falls short. The first and most direct approach is to model the internal structure of the Wolf-Rayet star itself, working inward from the observed surface properties to the hidden conditions at the core. This is the domain of stellar evolution codes, sophisticated computer programs that simulate the life of a star from birth to death, tracking the nuclear reactions, the energy transport, the chemical mixing, and the mass loss at every stage. The most widely used codes in this field include the Geneva Stellar Evolution Code, developed by Georges Maynet, André Maeder, and their colleagues at the University of Geneva over several decades, and the MESA code, Modules for Experiments in Stellar Astrophysics, developed by Bill Paxton and a large international team of collaborators starting around 2011, and now maintained as an open-source project used by hundreds of researchers worldwide. These codes take as inputs the initial mass, chemical composition, rotation rate, and mass loss prescription for a star, and they compute its evolutionary trajectory through time, predicting its luminosity, temperature, radius, and internal structure at every point from the zero-age main sequence to the final collapse. For a star that will become a WC8 Wolf-Rayet star like the one in Gamma Velorum, the evolutionary models tell a dramatic story. The star begins its life on the main sequence as a hot, luminous O-type star, fusing hydrogen to helium in its core through the carbon-nitrogen-oxygen cycle. This hydrogen-burning phase lasts a few million years, during which the star is stable, gradually increasing in luminosity as the mean molecular weight of its core increases. When the core hydrogen is exhausted, the star begins to restructure itself. The core contracts and heats up, and a hydrogen-burning shell ignites around the core, depositing fresh helium onto the growing helium core. The star expands, becoming a blue supergiant or, if massive enough, and if the conditions are right, a luminous blue variable, an unstable star prone to dramatic eruptions that eject large amounts of mass in brief, violent episodes. The most famous luminous blue variable is Eta Carinae, which underwent a spectacular eruption in the 1840s known as the Great Eruption, briefly becoming one of the brightest stars in the sky and ejecting roughly 10 to 20 solar masses of material in a few decades. During this expansion and mass loss phase, the outer hydrogen envelope is progressively stripped away. First, the surface composition changes as the products of nuclear burning are exposed. Nitrogen, produced by the carbon-nitrogen-oxygen cycle of hydrogen burning, appears at the surface, creating a WN-type Wolf-Rayet spectrum. Then, as stripping continues and the helium-burning core is revealed, carbon and oxygen appear, and the star transitions to a WC-type spectrum. The transition from WN to WC is not always smooth or well-defined. Some stars may pass through transitional stages, showing a mixture of nitrogen and carbon lines, and the details of the transition depend sensitively on the mass loss rate, the rotation rate, and whether the star is in a binary system where mass transfer can supplement wind-driven mass loss. The models predict that by the time a star reaches the WC8 stage, its core should be dominated by a mix of carbon, oxygen, and residual helium, with the relative proportions depending on how far advanced the helium burning has progressed. Core temperatures should be in the range of several 100 million to over 1 billion degrees Celsius. And critically, the mass of the core, which for a stripped Wolf-Rayet star is essentially the entire remaining star since the envelope has been removed, determines whether the eventual collapse will produce a neutron star or a black hole. For a total remaining mass of roughly 9 solar masses, and accounting for additional mass loss through winds in the final stages, the core mass at the moment of collapse is likely in the range of 5 to 8 solar masses. This places the remnant squarely in the uncertain zone between neutron star and black hole formation. The maximum mass of a neutron star is roughly 2 to 2.5 solar masses, set by the poorly understood equation of state of nuclear matter at extreme densities. If the collapsing core exceeds this limit and cannot halt its collapse, it will continue shrinking past the neutron star stage and form a black hole. The difference matters enormously because the type of remnant affects the energy, geometry, and observable properties of the supernova explosion. But here is where the model predictions begin to diverge, and where the limitations of our theoretical understanding become most apparent. Different stellar evolution codes, using different prescriptions for mass loss, convective mixing, rotational effects, and nuclear reaction rates, produce significantly different final core masses for the same initial conditions. The Geneva models, which include the effects of stellar rotation and the mixing of material driven by rotational instabilities, tend to produce more massive cores at the end of the Wolf-Rayet phase than non-rotating models. This is because rotation drives additional mixing of fresh fuel into the burning core, prolonging the nuclear burning phases and building up a larger reservoir of heavy elements. MESA models, depending on the input physics chosen by the user, which includes parameters for convective boundary mixing, known as overshooting, and for the treatment of semiconvective and thermohaline mixing, can produce results that agree with Geneva or diverge from it substantially. The spread in predicted final core masses across different models can be as large as 2 to 3 solar masses, which is enough to swing the prediction from a neutron star remnant to a black hole remnant and back again. The models are powerful tools, invaluable for understanding the broad sweep of stellar evolution, but they are not prophets. They are limited by our understanding of the input physics and some of the most critical physics, particularly the treatment of convective boundary mixing, magnetic fields, and the detailed effects of binary interaction, remains poorly constrained by observation. The second approach to understanding Gamma Valorum's fate focuses not on the interior of the star, but on its wind, the observable outflow that carries material away from the star and into space. The wind is the star's signature, its fingerprint, and by studying it in exquisite detail, astronomers hope to constrain the star's current state and predict its future. The primary tool for wind studies is spectroscopy, the analysis of the star's light broken into its component wavelengths. Wolf-Rayet emission lines are not simple features. They are broad, extending over several nanometers of wavelength, complex in profile shape, and shaped by the velocity field, density structure, and chemical composition of the entire outflow from the stellar surface out to distances of many stellar radii. By fitting synthetic spectra generated by atmospheric modeling codes such as CMF-GEN, developed by John Hillier at the University of Pittsburgh, or POWR, the Potsdam Wolf-Rayet code, developed by Wolf Rainer Hamann and his group at the University of Potsdam, to the observed spectrum of the star, astronomers can derive the wind's terminal velocity, mass loss rate, chemical abundances, ionization structure, and degree of clumping. For the Wolf-Rayet star in Gamma Velorum, spectroscopic analysis has revealed a wind terminal velocity of approximately 1,500 kilometers per second, a mass loss rate, corrected for clumping, of roughly 1.5 times 10 to the negative fifth solar masses per year, and a surface composition dominated by helium, carbon, and oxygen with no detectable hydrogen. The absence of hydrogen confirms that the star has been completely stripped of its original envelope. The carbon-to-helium ratio at the surface provides a kind of clock, indicating how deep into the helium-burning shell the stripping has progressed. For Gamma Velorum, the observed carbon abundance suggests that a significant fraction of the original helium has already been converted to carbon through the triple alpha process and subsequent carbon-12 plus helium-4 reactions, placing the star well into the late WC phase of its evolution. But the uncertainties in the spectroscopic modeling are substantial and must not be underestimated. The clumping factor, a parameter that describes how fragmented the wind is, must be assumed or fitted rather than measured directly, and different assumptions lead to different mass loss rates by factors of 2 or 3. The geometry of the wind, assumed to be spherically symmetric in most models, is actually distorted by the companion star's gravitational and radiative influence, creating density enhancements in the direction of the companion and density depletions in other directions. The ionization balance of the wind, which determines which spectral lines are produced and how strong they are, depends on the detailed radiation field, which is itself affected by the clumping and geometry. All of these factors introduce systematic errors into the derived parameters that are difficult to quantify and even more difficult to eliminate. The math is striking. Even with the revised lower mass loss rates, the Wolf-Rayet star in Gamma Velorum is losing roughly 1 Earth mass every 60 days to its stellar wind. Over the remaining lifetime of the Wolf-Rayet phase, which might be 100,000 to 300,000 years, this amounts to an additional 1 to 3 solar masses lost to space. If the star currently has 9 solar masses and will lose another 2 solar masses before it explodes, it will have a pre-supernova mass of roughly 7 solar masses, which after the explosion will leave a remnant of perhaps 2 to 3 solar masses squarely in the neutron star range. But if the current mass is higher than 9 solar masses, as some models suggest, or if the remaining wind mass loss is lower than expected, or if the final stages of nuclear burning proceed differently than the models predict. The remnant could be heavier, pushing into the uncertain zone between neutron stars and black holes. The margin between these outcomes is uncomfortably thin, and the observational uncertainties are uncomfortably wide. We are trying to predict the future of a star to within a solar mass or two, and our best measurements are uncertain by a solar mass or two. The overlap between prediction and uncertainty is almost total. The third approach to the Gamma Velorum problem comes from X-ray astronomy and the detailed study of the wind collision zone. As we discussed in the previous section, the region where the two stellar winds collide produces hot, shocked plasma that emits X-rays. By studying these X-rays in detail, astronomers can probe the dynamics of the collision, the densities and temperatures of the shocked gas, and the geometry of the interaction region. This information, in turn, constrains the properties of both winds and thus the properties of both stars. The Chandra X-ray Observatory has been particularly valuable for this work, thanks to its exceptional angular resolution of about half an arcsecond and the spectral capabilities of its high-energy transmission grating spectrometer, known as HET-GS. Observations of Gamma Velorum with Chandra's HET-GS, published in the early 2000s by teams led by researchers including Michael Schild, Werner Schmutz, Andy Pollock, and others, revealed a rich X-ray emission line spectrum with lines from highly ionized silicon, sulfur, argon, calcium, and iron. These are the spectral fingerprints of gas heated to tens of millions of degrees. Gas that exists only because two stellar winds are slamming into each other at thousands of kilometers per second. The line profiles, the shapes of the emission lines in wavelength space, encode information about the velocity field and geometry of the emitting region. A line from gas moving toward the observer is shifted to shorter wavelengths, blue shift, while gas moving away is shifted to longer wavelengths, red shift. The total profile of an emission line from the wind collision zone reflects the distribution of velocities in the shocked gas, which in turn depends on the geometry of the shock, the viewing angle, and the orbital phase. For Gamma Velorum, the line profiles observed by Chandra are consistent with emission from a conical shock region located between the two stars, with the cone opening angle and the shock standoff distance broadly agreeing with theoretical predictions based on the wind momentum ratio. However, the detailed shapes of the line profiles often disagree with the models at a level that suggests our understanding of the shock structure is incomplete. The models assume smooth flows and well-defined shock surfaces, but the real collision zone is turbulent, clumpy, and subject to instabilities that fragment the shock into a complex, time-varying structure. The fourth approach is infrared and radio astronomy, which probes the outer reaches of the stellar winds and the remarkable process of dust formation in the system. Infrared observations at wavelengths from about 1 to 25 microns have revealed excess emission beyond what the bare stellar photospheres would produce, indicative of warm dust in the system. The presence of dust near a star, with a surface temperature of 57,000 degrees, might seem impossible. How can solid particles survive in an environment of such extreme heat? The answer lies in the geometry of the wind collision zone. Behind the shock, in the downstream flow where the two winds have collided and been compressed, the gas cools as it expands away from the hottest part of the interaction region. In carbon-rich Wolf-Rayet systems like Gamma Velorum, where the wind is rich in carbon and helium but depleted in hydrogen, this cooling gas can reach temperatures low enough for carbon atoms to condense into tiny grains of amorphous carbon, essentially soot, similar in composition to the carbon black used in industrial processes on Earth. These dust grains are carried outward by the wind, forming a trailing spiral pattern that reflects the orbital motion of the binary system. As the two stars orbit each other, the dust-forming region behind the wind collision shock traces out a spiral in the orbital plane, like water from a spinning garden sprinkler. In some WC binaries with longer orbital periods, particularly the system WR104 in the constellation Sagittarius, this spiral dust pattern has been directly imaged using infrared interferometry at the Keck Observatory, creating one of the most beautiful and eerie structures in all of astronomy. The Pinwheel Nebula of WR104, first imaged by Peter Toothill, John Monnier, and William Danchi in 1999, shows a nearly perfect Archimedean spiral of glowing dust unwinding from the binary, its geometry revealing the orbital motion and wind properties of the system with stunning clarity. For Gamma Velorum, direct imaging of the dust spiral has been more challenging due to the system's shorter orbital period and the correspondingly smaller spatial scale of the spiral pattern on the sky. A 78-day orbit produces tighter spiral turns than a 200-day orbit, and the individual turns are more difficult to resolve with current infrared imaging technology. But infrared observations have confirmed the presence of heated dust in the system, and spectroscopic measurements have detected the characteristic emission features of amorphous carbon grains. Models suggest that Gamma Velorum does produce a dust spiral, albeit one that is less prominent than those of longer-period WC binaries, and the dust production rate is estimated at roughly 10 to the negative ninth to 10 to the negative 8 solar masses per year, far less than the gas mass loss rate, but significant in terms of the system's contribution to the interstellar dust budget. The dust production has implications that extend far beyond the Gamma Velorum system itself. Carbon dust is one of the key building blocks of the interstellar medium, the diffuse gas and dust that fills the space between stars and provides the raw material from which new stars and planets form. Wolf-rayet stars, and particularly carbon-rich WC stars like the one in Gamma Velorum, are significant contributors to the galaxy's carbon dust budget. Observations of the Milky Way's interstellar medium show that carbon-rich dust is ubiquitous, coating the surfaces of silicate grains, forming the backbones of complex organic molecules, and contributing to the extinction, the dimming, of starlight by scattering and absorbing photons. Some of this dust was produced in the cool outer atmospheres of evolved red giant stars through a similar but slower process of grain condensation. But some of it comes from the violent wind collision zones of WC binary systems forged in the space between dying giants and launched into the interstellar medium at high speed. Every grain of soot produced in the wind collision zone of Gamma Velorum will eventually drift into the general interstellar medium, mix with other gas and dust, and potentially be incorporated into a future generation of stars and planets. The carbon in your body, the carbon in the graphite of a pencil, the carbon in a diamond, some fraction of that carbon may have been forged in the core of a Wolf-rayet star and expelled through exactly the kind of violent wind process we see in Gamma Velorum today. The connection between the death of massive stars and the existence of rocky, carbon-based worlds like Earth is not metaphorical. It is chemical, it is direct, and it is quantifiable. The fifth and most recent approach brings together all of the above into comprehensive, multi-wavelength models of the Gamma Velorum system. These are ambitious, large-scale computational projects that attempt to simulate the entire binary system self-consistently, including both stellar winds, their collision, the shock structure, the particle acceleration, the dust formation, and the resulting radiation across the entire electromagnetic spectrum, from radio waves to X-rays. Such models require enormous computational resources and sophisticated numerical techniques. Three-dimensional hydrodynamic simulations are needed to capture the complex, time-dependent flow structure of the colliding winds. Monte Carlo radiative transfer calculations are needed to predict the emergent spectrum from the system, accounting for the absorption and scattering of photons by the dense stellar winds. And particle-in-cell simulations or diffusion equation solvers are needed to model the acceleration of electrons and protons in the shock region and to predict the resulting non-thermal emission. Groups at the University of Leeds, the University of Sheffield, Monash University in Australia, and several other institutions have made significant progress on these models over the past 2 decades. For Gamma Velorum specifically, three-dimensional hydrodynamic simulations have revealed that the wind collision zone is far more dynamic and structured than the idealized, two-dimensional models of earlier decades had suggested. The conical shock surface is subject to various instabilities that fragment and distort it on timescales much shorter than the orbital period. The Kelvin-Helmholtz instability, which arises from the velocity shear between the shocked gas and the unshocked wind flowing past it, creates ripples and vortices along the shock boundary. The nonlinear thin shell instability, which affects thin, compressed layers of gas between two opposing pressure sources, fragments the shock layer into filaments, clumps, and knots that move, merge, and dissolve on timescales of hours to days. These instabilities create a turbulent, chaotic collision zone that is far from the smooth, well-defined shock surface depicted in textbook diagrams. The real collision zone is a seething mass of hot and cool gas, threaded by magnetic fields, populated by accelerated particles, and constantly reshaped by the ever-changing balance of forces between the two winds. The simulations also show that the orbital eccentricity plays a crucial role in the system's behavior during periastron passage, when the stars are closest together at a separation of about 0.6 astronomical units. The collision zone is compressed between the two stars. The increased density leads to stronger radiative cooling, which may actually reduce the X-ray emission despite the higher wind velocities and collision energies. The periastron passage may also suppress particle acceleration by increasing the radiative losses that compete with the diffusive shock acceleration process. During apastron, when the stars are farthest apart at about 1.2 astronomical units, the collision zone expands and the gas density decreases. The lower density reduces radiative cooling, allowing the shocked gas to remain hotter for longer and potentially enhancing the X-ray emission. The apastron phase may also favor dust formation in the downstream cooling flow, because the lower density and lower radiation field allow the gas to cool more efficiently to the temperatures needed for grain condensation. The system breathes, pulsing between these extremes every 78.5 days, never reaching a true steady state, always in transition between compression and expansion. But even these sophisticated models have limitations that must be acknowledged with honesty. They necessarily simplify certain aspects of the physics, either because the full physics is computationally intractable or because the relevant parameters are not known with sufficient precision. They discretize the equations on finite computational grids, which limits the smallest structures they can resolve and may miss important processes that occur on scales smaller than the grid spacing. They make assumptions about subgrid processes, such as the rate of turbulent mixing and the efficiency of particle acceleration, that cannot be verified from first principles, and they are only as good as their input parameters, which include the mass loss rates, wind velocities, chemical compositions, and orbital elements of both stars, all of which carry the observational uncertainties we have discussed at length. Where does this leave us? After decades of observation and modeling, the Gamma Velorum system remains a problem that is partially solved but deeply uncertain in its most important details. We know that it is a close binary containing a WC8 Wolf-Rayet star and an O-type companion. We know the orbital period, the eccentricity, the approximate masses and luminosities of both stars. We know that the winds collide to produce hot, X-ray emitting plasma, and that dust forms in the cooling outflow behind the shock. We know that the Wolf-Rayet star is losing mass rapidly and will eventually exhaust its nuclear fuel and collapse. But we do not know the precise mass of the Wolf-Rayet star to better than about 20 to 30%. We do not know its mass loss rate to better than a factor of 2. We do not know whether it will produce a neutron star or a black hole when it dies. We do not know whether the explosion will be a standard type Ib or icy supernova, a more energetic hypernova, or something even more exotic. And we do not know, with confidence, whether the event will pose any risk to Earth, beyond the spectacular visual display it will certainly produce. The uncertainty is not a failure of science. It is an honest accounting of how much we still have to learn about the most extreme objects in our galaxy. There is a saying among astrophysicists that captures both the humility and the motivation of this field. The universe is under no obligation to make sense to us. The Gamma Velorum system embodies this truth. It is close enough to study in detail, bright enough to observe across the electromagnetic spectrum from radio waves to gamma rays, and dynamic enough to test our theories of stellar winds, shocks, particle acceleration, and dust formation in real time. And yet it continues to surprise us, to resist simple explanations, to demand more sophisticated models and more precise observations. It is a laboratory, a challenge, and a warning, all wrapped in a single point of light in the southern sky. And the most important thing it has to teach us may be something we have not yet learned to ask about. Let us now step back from the technical details and confront the larger reality of what Gamma Velorum represents. We have been speaking about mass loss rates and X-ray luminosities, about wind velocities and orbital parameters, as though these were abstract quantities in a physics textbook. But they are not abstract. They describe a physical event that is happening right now, at this very moment, in a specific location in our galaxy, a location close enough that light from it reaches your eyes in just over 1,000 years. The Wolf-Rayet star in Gamma Velorum is dying. It is not dying metaphorically. It is not dying in some distant academic sense. It is a star that has already shed more than 3/4 of its original mass, exposed its bare nuclear-burning core to the vacuum of space, and is now in the final stages of a process that will end in one of the most violent events in nature, and it is our neighbor. In a galaxy 100,000 light-years across, containing hundreds of billions of stars, the nearest and brightest Wolf-Rayet system happens to sit just over 1,000 light-years away. That is roughly 1% of the diameter of the galaxy. In the vastness of the Milky Way, Gamma Velorum is practically next door. This is not science fiction. This is a star catalogued in databases, observed by telescopes, studied in peer-reviewed journals published in the Astrophysical Journal, monthly notices of the Royal Astronomical Society, and Astronomy and Astrophysics. Its light arrives at Earth, having travelled roughly 1,090 light-years, which means that what we see when we look at Gamma Velorum tonight is the state of the system approximately 1,090 years ago, around the year 936 in the Common Era, when the Viking Age was at its height in Europe, when the Song dynasty was consolidating power in China, when the great civilizations of the medieval world were reshaping the continents. The star may have changed significantly since then. It may have already begun the final stages of silicon burning in its core, the brief, furious nuclear process that produces iron and signals the end, or it may have hundreds of thousands of years left. We cannot know. We see only the past. And the future of this system, whatever it holds, is already determined by physical processes that are underway right now. Processes that light has not yet carried to us. Processes that we can describe with equations, but cannot influence in any way. Let that sink in. Consider what will happen when the Wolf-Rayet star finally exhausts its fuel. The sequence of events is well understood in outline, though the details remain uncertain and are the subject of intense ongoing research. Deep in the core, nuclear fusion will proceed through progressively heavier elements, each stage burning faster than the last. Hydrogen burning took a few million years. Helium burning takes a few 100,000 years. Carbon burning takes a few hundred to a few thousand years. Neon burning takes roughly a year. Oxygen burning takes a few months. And silicon burning, the final stage, takes roughly 1 day. One single day. After millions of years of stellar evolution, after hundreds of thousands of years of violent self-destruction as a Wolf-Rayet star, after centuries of carbon burning and months of oxygen burning, the final chapter is compressed into 24 hours. The acceleration is breathtaking. Each successive burning stage produces less energy and consumes fuel faster, like a fire burning through smaller and smaller piles of kindling with increasing desperation. And at the end of that final day, the core is made of iron. Iron is the end of the line. Fusing iron does not release energy, it absorbs energy. The nuclear reaction that produces elements heavier than iron is endothermic, meaning it takes more energy to make it happen than it gives back. The star has built a dead core, an inert ball of iron at its center, and there is no more fuel to burn, no more energy to produce, no more pressure to push back against gravity. What happens next takes less than a second. The iron core, no longer supported by the outward pressure of nuclear reactions, collapses under its own gravity. The collapse happens at roughly 1/4 of the speed of light, about 70,000 kilometers per second. Electrons are forced into protons, producing neutrons and releasing neutrinos, ghostly particles that barely interact with matter and can pass through light years of solid lead without stopping. The core, which moments ago was roughly the size of the Earth, about 12,000 kilometers across, is compressed into a sphere less than 20 kilometers in diameter. The density in this collapsing core exceeds 100 billion kilograms per cubic centimeter, a density so extreme that a teaspoon of the material would weigh more than all the water in Lake Michigan. At this density, matter behaves in ways that push the boundaries of known physics, becoming a fluid of neutrons governed by the strong nuclear force and quantum mechanics. The neutrino burst produced during the core collapse is staggering. More energy is carried away by neutrinos in 10 seconds than the Sun will produce in its entire 10 billion year lifetime. Let that sink in. 10 seconds of neutrino emission from a collapsing core carries more energy than 10 billion years of sunlight. The overwhelming majority of the energy released in a supernova is not in the light, not in the shockwave, not in the blast of cosmic rays. It is in the neutrinos. The visible explosion, spectacular as it is, represents less than 1% of the total energy budget. The neutrinos carry away 99% of the gravitational binding energy of the newly formed neutron star, roughly 3 times 10 to the 46 joules, streaming outward through the collapsing star as though it were transparent. Because for neutrinos, ordinary matter is indeed almost perfectly transparent. The outer layers of the star, still falling inward at tens of thousands of kilometers per second, crash into the newly formed neutron core and bounce. This bounce, aided by the neutrino energy deposition in the layers just above the neutron star, and by various hydrodynamic instabilities, including the standing accretion, shock instability, and convective overturn, drives a shock wave outward through the infalling material. The shock wave heats the infalling gas to billions of degrees, triggering a cascade of nuclear reactions that synthesize elements heavier than iron, gold, platinum, uranium, and dozens of others through rapid neutron capture processes known as the R process. The shock breaks through the surface of the star, and the supernova is born. For a few weeks, the exploding star will shine with a luminosity of roughly 10 billion suns, briefly outshining the entire galaxy in which it resides. The material expelled by the explosion will expand outward at velocities of 10,000 to 30,000 kilometers per second, sweeping up interstellar gas and creating a supernova remnant that will be visible for tens of thousands of years. For Gamma Velorum, the supernova of the Wolf-Rayet component would be visible from Earth as a new star appearing in the constellation Vela, suddenly and without warning. At a distance of 1,090 light-years, the apparent brightness of the supernova would depend on the total luminosity and the amount of interstellar dust between us and the explosion. For a typical Type Ib or Type IC supernova, which is the kind expected from a Wolf-Rayet star that has been stripped of its hydrogen envelope and possibly much of its helium, the peak apparent magnitude could reach roughly -6 to -8. For comparison, Venus at its brightest is about magnitude -4.6, and the full moon is about magnitude -12.7. The supernova would be several times brighter than Venus and easily visible in daylight. It would cast visible shadows at night. For weeks, it would be the most prominent object in the sky, apart from the sun and the moon, and then, over the course of months, it would fade, leaving behind an expanding nebula of gas and dust, enriched with heavy elements, and at the center, a compact remnant, either a neutron star spinning hundreds of times per second, or a stellar mass black hole, dark and silent. The event would not announce itself with light first. It would announce itself with neutrinos, because neutrinos interact so weakly with matter, they escape the collapsing core within seconds, while the light from the explosion takes hours to diffuse through the expanding stellar debris and reach the surface. For a supernova at the distance of Gamma Velorum, roughly 1,090 light-years, modern neutrino detectors would register the event several hours before the first photons of visible light appeared. The Super Kamiokande detector in Japan, a 50,000 tank of ultra-pure water monitored by thousands of photomultiplier tubes buried under Mount Ikino, would detect thousands of neutrino interactions from a supernova at this distance, compared to the 11 events it would have seen from the famous SN 1987A in the Large Magellanic Cloud, which was 168,000 light-years away. the Ice Cube Neutrino Observatory at the South Pole, which instruments a cubic kilometre of Antarctic ice with over 5,000 optical sensors, would see a dramatic burst of neutrino-induced light spreading through the ice. The deep underground liquid argon detectors of the Deep Underground Neutrino Experiment, or DUNE, currently under construction at the Sanford Underground Research Facility in South Dakota, would provide detailed information about the energy spectrum and flavor composition of the neutrino burst, constraining the physics of the collapse in ways that light alone never could. The supernova would also be a gravitational wave source. The asymmetries in the core collapse, the convective overturn, the standing accretion shock instability, and the formation of the compact remnant all generate gravitational radiation, ripples in the fabric of space-time that propagate outward at the speed of light. For a supernova at 1,000 light-years, advanced gravitational wave detectors such as LIGO, Virgo, and CAGRA would detect a clear signal, providing direct information about the dynamics of the collapse and the formation of the remnant. The combination of neutrino data, gravitational wave data, and electromagnetic observations across the entire spectrum from radio to gamma rays would make a gamma velorum supernova one of the most thoroughly observed astrophysical events in human history, a multi-messenger bonanza that would test our models of core collapse, nucleosynthesis, and compact object formation with unprecedented precision. Astronomers have prepared for this possibility. The Supernova Early Warning System, known as SNELUS, is a network linking the world's major neutrino detectors, designed to issue an automatic alert to observatories worldwide within minutes of detecting a galactic supernova neutrino burst, giving telescopes time to slew toward the source before the visible light arrives. For a star as well studied as Gamma Velorum, with a known position, known distance, and known progenitor properties, the scientific yield from such an event would be transformative. But the supernova itself, as spectacular as it would be, is not the most concerning possibility. The deeper truth, the one that has occupied a particular subset of astrophysicists and planetary scientists, involves the possibility of a gamma-ray burst. Gamma-ray bursts are the most energetic electromagnetic events in the universe, after the Big Bang itself. They come in two varieties: short bursts lasting less than 2 seconds, produced by the mergers of neutron stars, and long bursts lasting from seconds to minutes, produced during the collapse of certain massive stars. Long gamma-ray bursts are what concern us here. They involve the formation of a rapidly spinning black hole, or magnetar, at the center of a collapsing star, which launches two narrow jets of matter and radiation along its rotational axis at velocities approaching the speed of light. The jets punch through the dying star and continue into space, producing a focused beam of gamma radiation that can be detected across billions of light years. The conditions required for a long gamma-ray burst are specific and not yet fully understood. The collapsing core must be rotating rapidly enough to form an accretion disk around the newly formed compact object. The progenitor star must have lost its hydrogen envelope, which Wolf-Rayet stars have by definition. Some theoretical models, particularly those developed by Stan Worsley at the University of California, Santa Cruz, require the star to have also lost most of its helium envelope, making WC stars better candidates than does. The metallicity of the progenitor, its content of elements heavier than hydrogen and helium, may also play a critical role, with lower metallicity stars being more likely to produce gamma-ray bursts, because their stellar winds are weaker, removing less angular momentum from the core and allowing it to retain the rapid rotation needed for jet formation. For Gamma Velorum, the Wolf-Rayet star is a WC type. It has lost its hydrogen envelope. Its helium envelope is being actively stripped by its wind and possibly by interaction with its companion. These match some of the prerequisites for a gamma-ray burst progenitor. However, the metallicity of Gamma Velorum is roughly solar, meaning it has a normal abundance of heavy elements for a star in this region of the Milky Way, and this is significantly higher than what most models predict is needed for a gamma-ray burst. High metallicity means stronger stellar winds, means more angular momentum lost over the star's lifetime, means a core that is likely rotating too slowly to form the accretion disk and jet system required for a burst. Additionally, tidal interactions with the companion star may have further slowed the core's rotation through gravitational coupling between the stars. The current scientific consensus is that Gamma Velorum is unlikely to produce a gamma-ray burst. The conditions are probably not right. The metallicity is probably too high. The rotation is probably too slow. But the word probably carries weight in a context where the consequences of being wrong are severe. A gamma-ray burst aimed at Earth from a distance of 1,090 light-years would deposit enough high-energy radiation into the upper atmosphere to destroy a significant fraction of the ozone layer, potentially 30 to 50% or more. The resulting increase in ultraviolet radiation at the surface would damage terrestrial and marine ecosystems, harm photosynthetic organisms, increase mutation rates, and potentially trigger a mass extinction event. Studies by Adrian Mellott, Brian Thomas, and others at the University of Kansas have suggested that gamma-ray bursts from within a few thousand light-years could have been responsible for at least one mass extinction in Earth's geological history, possibly the late Ordovician extinction roughly 445 million years ago. Though this hypothesis remains speculative and debated, the probability of a gamma-ray burst from Gamma Velorum being directed at Earth is small for two independent reasons. First, a gamma-ray burst, even if it occurs, will be emitted in two narrow jets, each with an opening angle of only a few degrees. The chance that one of those jets is aimed at Earth depends on the orientation of the Wolf-Rayet star's rotational axis, and there is no strong observational reason to believe that the axis points toward us. The solid angle subtended by the jet is a tiny fraction of the full sphere, typically 1% or less. Second, as discussed, the physical conditions in the star are probably not conducive to jet formation in the first place. The combined probability, a gamma-ray burst occurring and its jet being pointed at Earth, is estimated at well below 1%, possibly below 1/10%. But this is not zero, and in a field where our theoretical understanding of jet formation is incomplete, and our observational constraints on core rotation are essentially non-existent, even small probabilities deserve honest acknowledgement. The Gamma Velorum system does not exist in isolation. It is a member of the Vela OB2 Association, a group of young, massive stars that share a common origin, having formed from the same giant molecular cloud roughly 10 to 20 million years ago. The Vela OB2 Association spans several degrees on the sky and contains at least a few dozen O-type and early B-type stars, many of which will themselves end as supernovae over the coming millions of years. Understanding Gamma Velorum's context within this association is crucial because the collective effect of multiple massive stars, their ionizing radiation, their stellar winds, and their eventual supernovae shapes the structure and evolution of the surrounding interstellar medium on scales of hundreds of light years. The association itself has been studied in detail using data from the Gaia satellite, which provided precise distances and velocities for thousands of stars in the region. These studies, led by researchers including Eleonora Zari at Leiden Observatory and Tyler Cantat-Gordon at the University of Padova, have revealed that the Vela OB2 Association is not a single, cohesive group, but rather a complex, multi-component structure, with at least two distinct populations at slightly different distances. The nearer population, at roughly 1,000 light-years, appears to be associated with Gamma Velorum itself, and may represent the most recently formed generation of stars in the region. The more distant population, at roughly 1,200 to 1,300 light-years, may be slightly older and more dispersed. The relationship between these two populations is still debated. They may represent two episodes of star formation in the same molecular cloud, triggered at different times by different events, or they may be distinct groups that happen to overlap on the sky but have different origins. The environment surrounding Gamma Velorum bears the scars of past stellar violence with remarkable clarity. The region around Gamma Velorum is already scarred by the remnants of past stellar death. The Vela supernova remnant, one of the closest and most well-studied supernova remnants in the sky, lies in the same general direction, the result of a supernova that occurred roughly 11,000 years ago at a distance of about 800 light-years. At its center sits the Vela pulsar, a rapidly spinning neutron star that serves as proof of the violence that created it. The pulsar rotates approximately 11 times per second and emits beams of radio waves and gamma rays that sweep across our line of sight like a cosmic lighthouse. It was one of the first pulsars discovered, identified in 1968 by astronomers at the Molonglo Radio Observatory in Australia, just months after the discovery of the first pulsar by Jocelyn Bell Burnell and Anthony Hewish at Cambridge. The Vela pulsar's spin-down rate, the rate at which its rotation is slowing due to the loss of rotational energy through electromagnetic radiation and particle emission, provides an independent estimate of its age that is consistent with the age of the surrounding remnant, confirming that the two are products of the same event. The Gum Nebula, a vast faint emission nebula spanning roughly 36 degrees on the sky, is thought to be the ancient remnant of an even older supernova or series of supernovae in the same region, a fossil of explosions that occurred hundreds of thousands or millions of years ago. Its enormous angular size, corresponding to a physical diameter of roughly 1,400 light-years at its estimated distance, makes it one of the largest known structures in the nearby interstellar medium. The interior of the Gum Nebula is filled with hot, low-density gas that has been heated and ionized by the combined radiation of the massive stars within it, including Gamma Velorum itself and the nearby hot star Zeta Puppis, another bright O-type supergiant that is also losing mass through a powerful stellar wind. Gamma Velorum is embedded in a landscape of past catastrophes, and it will add its own contribution to that landscape when its time comes. The deep truth of Gamma Velorum is not just that a single star will explode. It is that massive stars are engines of cosmic change, operating on timescales that make human history seem vanishingly brief. The Wolf-Rayet star in Gamma Velorum has been shaping its environment for millions of years, first with its intense ultraviolet radiation, ionizing the surrounding gas and creating vast bubbles of hot, low-density plasma called wind-blown bubbles, then with its powerful stellar wind, sweeping up interstellar material into dense shells and triggering the formation of new stars at the compressed boundaries, a process known as triggered star formation, and eventually with its supernova, which will inject more energy into the surrounding medium in a few seconds than the star released in its entire multi-million-year life, seeding the region with heavy elements and accelerating particles to near the speed of light. The cycle continues. The heavy elements from the supernova will mix with the interstellar medium, enrich the next generation of molecular clouds, and become part of the next generation of stars and planets. Somewhere, millions of years from now, a rocky planet may form around a young star, incorporating atoms of carbon, oxygen, and iron that were forged in the core of WR11 and ejected in its death. Life may arise on that planet, built from those atoms, and it will have no way of knowing that the elements in its cells were once part of a dying star in the constellation Vela, a star that briefly caught the attention of a curious species on a small rocky world 1,000 light-years away. The death of Gamma Velorum's Wolf-Rayet star is not an ending, it is a beginning. But it is a beginning that requires destruction on a scale that challenges human comprehension, a beginning paid for in fire. What does all of this mean for us? Not for astrophysics, not for computational modeling, not for the next generation of space telescopes. What does it mean for us, as conscious beings living on a small rocky planet, orbiting an unremarkable star in the suburbs of a spiral galaxy? The question might seem indulgent. The Wolf-Rayet star in Gamma Velorum does not know we exist. It will not pause its self-destruction because we are watching. Its future is governed by the laws of nuclear physics and gravity, not by human concern or human anxiety. And yet the question matters, because the act of asking it is itself one of the most extraordinary things happening in this corner of the cosmos. A ball of plasma is tearing itself apart 1,000 light-years away, and here, on a tiny rock orbiting a modest star, collections of atoms have organized themselves into patterns complex enough to study that process, to model it, to predict its outcome, and to feel something about it. That, in its own way, is as remarkable as the star itself. We are made of the same stuff. This is not poetry. It is not a metaphor designed to make the cosmos feel more accessible. It is chemistry, verified by spectroscopy, confirmed by nucleosynthesis calculations, and traceable through the geological and chemical record of our planet. The oxygen in the air you breathe was forged in the cores of massive stars that lived and died billions of years before the sun was born. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of these elements were created inside stars through the same nuclear fusion processes that are occurring right now in the core of the Wolf-Rayet star in Gamma Velorum. When that star explodes, it will scatter these elements across light years of space, enriching the interstellar medium with the raw materials for new worlds, new oceans, new atmospheres, and potentially new life. We are not separate from this process. We are not observers standing outside the system, looking in through a window. We are part of it. We are one of its outcomes. The atoms in your body have been through at least one supernova, possibly several, before they came together in the cloud of gas and dust that collapsed to form the solar nebula 4.6 billion years ago. You are, in a very real and literal sense, made of dead stars. The iron in your hemoglobin, the molecule that carries oxygen in your blood, was produced in the final moments of a star's life, in the brief fury of silicon burning that precedes core collapse. You breathe because a star died. There is a pause that deserves to be taken here, a moment of quiet, not for mourning but for recognition. Every heavy element on Earth was produced in a stellar interior or a stellar explosion. Every molecule of water, every grain of soil, every strand of genetic material, all of it traces back to nucleosynthesis in environments of unimaginable heat and pressure. The gold in a wedding ring was created in the merger of two neutron stars, or in the supernova of a massive star, events that destroyed entire stellar systems while seeding the cosmos with the ingredients of. There is no creation without destruction at this scale. The universe builds complexity from catastrophe. It assembles order from chaos. It uses the deaths of giant stars as the delivery mechanism for the elements that make rocky planets and life possible. This is not a comforting story. It is not a fairy tale about a benevolent cosmos caring for its children. It is a story about physics, about thermodynamics, about the second law and its exceptions, about pockets of complexity arising in a universe trending toward equilibrium. Gamma Velorum is part of this machinery, one small gear in the vast, slow engine of cosmic chemical enrichment. Its death, when it comes, will be a tragedy by any human measure, a star that burned for millions of years, finally extinguished in a flash of light and neutrinos. But it will also be a gift, an injection of heavy elements into the galaxy that will eventually become part of something new, something that we cannot possibly predict. Consider the timescales involved. The Wolf-Rayet star in Gamma Velorum has perhaps a few 100,000 years left before it collapses. That could be 100,000 years. It could be 500,000. The uncertainty is itself a lesson in the limits of our knowledge, but in human terms, even the lower end of that range is an eternity. 300,000 years ago, Homo sapiens had just emerged as a distinct species in Africa. We had no agriculture, no writing, no cities, no concept of astronomy beyond the instinctive awe of the night sky. In 300,000 years from now, assuming our species or its descendants survive, we will be something unrecognizable to our current selves. Civilizations will have risen and fallen many times over. Technologies will have been invented that we cannot imagine and forgotten and reinvented. The continents will have shifted measurably, and the stars themselves will have moved noticeably against the background of more distant stars. And at some point during that vast span of future time, a light will appear in the southern sky, brighter than any star, brighter than Venus, visible in the daytime. It will grow in brightness over the course of days, reaching its peak within a week or two, and then slowly fade over weeks and months, leaving behind a faint, expanding cloud of glowing gas visible for centuries in long-exposure photographs. Whatever beings are alive on Earth at that moment will witness one of the most spectacular astronomical events in human history. Whether they will have the knowledge and the instruments to understand what they are seeing is another question entirely. Or perhaps no one will witness it at all. Perhaps our species will be gone by then, replaced by something else, or simply extinct. one of the countless experiments in complexity that the universe has run and discarded. This is not a morbid thought. It is a statistical observation. Most species that have ever existed on Earth are now extinct. The average lifespan of a mammalian species is roughly 1 to 2 million years. We have existed for about 300,000 years. If we follow the average, which is a crude but sobering benchmark, we have perhaps 1 million years left, give or take several 100,000. The supernova of Gamma Valorum's Wolf-Rayet star, at a few 100,000 years out, falls within the span of time during which our species might reasonably be expected to exist. We might be around to see it, we might not. The star does not care either way. It will explode regardless of whether anyone is watching. There is a second philosophical dimension here that deserves exploration, and it concerns the nature of knowledge itself, the remarkable and fragile edifice of understanding that our species has constructed over a few millennia. Everything we have discussed about Gamma Valorum, its mass, its luminosity, its wind, its companion, its eventual fate, has been determined by studying photons. Particles of light that left the system over 1,000 years ago travelled across the void of interstellar space at 299,792 kilometers per second and were collected by mirrors and detectors built by beings who did not even know what stars were made of until the early 20th century. The entire edifice of our understanding of this system rests on our ability to decode the information carried by light. We have never visited Gamma Valorum. We have never sent a probe. We will never touch it or sample it directly. Not in this century, not in this millennium, probably not ever. Everything we know from afar, by interpreting the faint signals that reach us across the vast emptiness between stars. And yet, from those signals, we have reconstructed the life story of a star. We know its approximate birth mass. We know its evolutionary history, the stages it has passed through, the layers it has shed. We know its current chemical composition, dominated by helium, carbon, and oxygen. We know its surface temperature to within a few thousand degrees, and the speed of its wind to within a few hundred kilometers per second. We know the period of its orbit to within a fraction of a day. This is an astonishing achievement of human intellect, perhaps one of the most impressive things our species has ever done, and it is almost entirely invisible to the general public. Most people have never heard of Gamma Valorum. Most people do not know what a Wolf-Rayet star is. Most people would not recognize the significance of what these observations represent. A species confined to a single planet, using instruments made of glass and silicon, reaching across 1,000 light-years of space to determine the internal nuclear processes of a dying star. If that is not a reason for awe, nothing is. But there is also humility in this story, and that humility is as important as the awe. For all that we have learned, we remain fundamentally uncertain about the most important questions. Will the supernova produce a neutron star or a black hole? We genuinely do not know. Will it produce a gamma-ray burst? Almost certainly not, but we cannot be completely sure. Will the explosion affect Earth in any meaningful way beyond the visual spectacle? Probably not, but the models carry uncertainties that we cannot fully quantify. We are like physicians who have identified a condition, understand its mechanism in general terms, and can describe its progression broadly, but cannot predict the exact moment of crisis or the precise outcome for a particular patient. The universe is more complex than our models, and Gamma Valorum, for all that we have studied it, retains its capacity to surprise us. This uncertainty is not a weakness of science. It is its defining strength. Science does not claim certainty where none exists. It quantifies uncertainty, identifies what is known and what is not, and works systematically to reduce the gap between them. The story of Gamma Valorum is a story of that process, a decades-long effort by hundreds of astronomers around the world to understand a single stellar system, and through it, to understand the fate of all massive stars everywhere. And so we return to where we began, a point of light in the southern sky, faintly blue-white, steady, unremarkable to the casual observer, just one of the thousands of visible stars, a fleck of brightness in the ancient constellation of the Sails. But now you know what that light contains. You know that behind that quiet glow lies a system of extraordinary violence and beauty. two massive stars locked in an orbital embrace, one of them tearing itself apart, shedding its mass into space at thousands of kilometers per second, exposing its bare, burning core to the universe. You know that where their winds collide, temperatures reach tens of millions of degrees, producing X-rays and accelerating particles to nearly the speed of light. You know that dust condenses in the cooling wake of that collision, tiny grains of carbon soot that spiral outward like the arms of a miniature galaxy, carrying the raw materials for future worlds. And you know that this system is finite, that it has a beginning and will have an end. And that end will be one of the most spectacular events in the recent history of our galaxy. Gamma Velorum is a mirror, not in the optical sense, but in the existential one. It shows us what we are made of and what awaits us. Every atom of carbon in the biosphere was once inside a star. Every molecule of water on Earth contains oxygen that was forged in nuclear fire. The iron at the core of our planet was produced in the final stages of silicon burning in a massive star. The same process that is approaching its conclusion in the Wolf-Rayet star of Gamma Velorum. We are star stuff contemplating star death. We are temporary configurations of matter and energy that have become complex enough to understand our own origins and our own impermanence. The star does not know this. It cannot know this. It is a sphere of plasma governed by the equations of hydrodynamics and nuclear physics, with no awareness, no intention, no concern for the observers who watch it from 1,000 light years away. And yet its existence matters to us, not because it threatens us, not merely because it will produce a visible supernova in some distant future, but because it teaches us something about the nature of the universe we inhabit. It teaches us that the cosmos is not a static backdrop to human affairs. It is a dynamic, evolving, violent, and creative system, building and destroying on scales that dwarf our entire civilization. The Wolf-Rayet phase is a reminder that nothing in the universe is permanent. Not stars, not galaxies, not the elements themselves, which are created and destroyed in the furnaces of stellar interiors and the crucibles of supernova explosions. Our sun, the star that sustains all life on Earth, is itself temporary. It will exhaust its hydrogen fuel in roughly 5 billion years, swell into a red giant engulfing Mercury and Venus and possibly Earth, and eventually shed its outer layers to become a white dwarf, a fading ember in the darkness. It will never become a Wolf-Rayet star. It is too small. It will never explode as a supernova. It lacks the mass, but it shares the same fundamental fate as Gamma Velorum's dying star. All stars end. All fires go out. The only question is how and when and what they leave behind. If the sun were the size of a grain of sand, placed on the tip of your finger, then Gamma Velorum would be another grain of sand, roughly 120 meters away, across the length of a football field and beyond. But that second grain of sand would be glowing with the intensity of 200,000 tiny suns, a speck of matter pouring energy into space with a ferocity that defies ordinary description. And it would be shrinking measurably, losing mass to a wind that never stops, wearing itself down over the course of a few 100,000 years. 2 grains of sand separated by the length of a football field, one of them quiet and steady, the other burning itself alive. That is the relationship between our star and the dying giant in Vela. It is the relationship between stability and extremity, between endurance and brilliance, between a star that will burn for billions of years and one that will expire in a cosmic instant. And beyond these 2 grains of sand, stretching in every direction to unimaginable distances, lies the galaxy. A disk of 200 to 400 billion such grains, most of them smaller and dimmer than our sun, a few of them larger and brighter, and a very few of them in the extraordinary, doomed state of Gamma Velorum. The Milky Way contains perhaps 1,000 to 2,000 Wolf-Rayet stars at any given time, out of hundreds of billions of stars total. They are rare, they are fleeting, and they are among the most important objects in the universe, because they are the primary engines of chemical enrichment at high masses, the sources of the heavy elements that make rocky planets, organic chemistry and biology possible. Without Wolf-Rayet stars, without the supernovae that end their lives, without the winds that disperse their processed material into the interstellar medium, the universe would remain a monotonous sea of hydrogen and helium, with no carbon, no oxygen, no iron, no silicon, no possibility of anything resembling the complexity we call life. Every grain of carbon soot expelled by Gamma Velorum, every atom of oxygen mixed into the interstellar medium by its ferocious wind, is a contribution to the chemical inventory of the galaxy. It is an investment in future complexity, paid for in the currency of stellar death. The study of Gamma Velorum has shaped not just our understanding of this particular system, but our understanding of massive stars and their deaths more broadly. Lessons learned from modelling the wind collision zone of Gamma Velorum have been applied to dozens of other colliding wind binaries throughout the galaxy. Techniques developed to measure the mass loss rate of its Wolf-Rayet component and the clumping corrections required to make those measurements accurate have become standard tools applied to all Wolf-Rayet and O-type stellar winds. The distance controversy, resolved by Gaia but only after 2 decades of confusion, has made the entire field more cautious about accepting satellite measurements at face value and more diligent about understanding the systematic errors that lurk in even the most sophisticated astrometric catalogues. In a very real sense, Gamma Velorum has been a teacher. Its proximity and brightness have made it the proving ground for ideas that are then applied to more distant, fainter, less accessible systems. If we can understand this binary, we have a chance of understanding the hundreds of other Wolf-Rayet binaries scattered throughout the Milky Way and the neighbouring Magellanic Clouds. If we cannot understand it, despite decades of effort and billions of dollars of telescope time, then we must confront the possibility that our theoretical framework is missing something fundamental. The next generation of telescopes and instruments promises to push our understanding further. The James Webb Space Telescope, launched in 2021, provides infrared sensitivity and angular resolution that surpasses anything previously available, enabling detailed studies of the dust formation in the wind collision zone and the chemical composition of the stellar winds at wavelengths previously inaccessible. Ground-based extremely large telescopes, including the European Extremely Large Telescope under construction in Chile, will provide angular resolution in the optical and near-infrared that rivals or exceeds that of space-based observatories, potentially allowing direct imaging of the wind collision structure for the first time. And the continued operation of X-ray observatories, combined with the development of next-generation missions with improved spectral resolution and collecting area, will enable more precise measurements of the temperature, density, and velocity structure of the shocked gas, testing our models against reality with ever greater fidelity. Gamma Velorum will remain at the forefront of massive star research for decades to come, not because we have run out of other systems to study, but because this one, the brightest, the closest, the most thoroughly observed, continues to reveal new layers of complexity every time we look at it with better eyes. Gamma Velorum, the brightest Wolf-Rayet system in our sky, the closest example of this extraordinary class of dying star, sits tonight where it has sat for centuries, glowing softly in the constellation of the Sails. It will be there tomorrow night, and the night after that, and for a very long time to come by human standards. But not forever. Nothing is forever. The light you see from Gamma Velorum is a message from the past, a record of what the system looked like 1,000 years ago. The light the system is producing right now, at this very instant, will not reach Earth for another 1,000 years. Observers alive in the year 3100 will see the Gamma Velorum of today, and at some point in the future, whether tens of thousands of years from now or hundreds of thousands, the nature of that light will change. A pulse of neutrinos will arrive first, traveling at nearly the speed of light, detectable by underground neutrino observatories like Super Kamiokande in Japan, signaling that the core has collapsed, that the end has come. Hours later, the optical brightening will begin as the shockwave breaks through what remains of the star's surface. A new point of light will appear in Vela, growing brighter over the course of days, outshining everything in the night sky except the moon. Astronomers will rush to point every available telescope at the event. Papers will be published within hours. Models will be tested against observation for the first time. And for a few brief weeks, the death of a star will command the attention of the entire world. Then it will fade. The new star will dim month by month until it slips below naked eye visibility. The expanding nebula will glow for centuries, a faint shell of gas visible in long exposure photographs and studied by generation after generation of astronomers, slowly merging with the interstellar medium. The compact remnant at the center, neutron star or black hole, will be studied for decades. And eventually, the event will become another entry in the astronomical record, another data point in the long history of stellar death and renewal that has shaped this galaxy for 13 billion years. But the atoms will endure. The carbon, oxygen, and iron forged in the core of WR11, ejected by the supernova, dispersed by the expanding remnant, will drift through interstellar space for millions of years. They will be swept up by passing shock waves, compressed into molecular clouds, folded into the cores of collapsing protostars. They will become part of new stars and new planets, part of new oceans and new atmospheres, and perhaps, in some unimaginably distant future, they will become part of something that looks up at the sky and wonders what it is made of. That is the legacy of Gamma Velorum. Not the violence, not the spectacle, not the terrifying possibility of a supernova visible in daylight. The legacy is the continuity, the fact that nothing is truly lost, only transformed, recycled, reimagined by a universe that has been doing this for almost 14 billion years and shows no sign of stopping. Tonight, if you are in the southern hemisphere, step outside and find the constellation Vela. Look for the bright blue-white star near the False Cross, the one that ancient sailors used to navigate the dark waters of the southern seas. That star is Gamma Velorum. That star is a dying giant, shredding itself to pieces, locked in a gravitational waltz with a companion nearly as extreme as itself, producing shocks and dust and X-rays and cosmic rays in the narrow space between them. It is beautiful. It is doomed. It is the closest Wolf-Rayet system to Earth, and it is one of the most important objects in the sky for understanding how the universe builds complexity from simplicity, how it creates the conditions for life by destroying its largest and most luminous stars. Look at it carefully. It will not last, but neither will we, and perhaps that is the deepest thing it has to teach us. Not that the universe is vast, or violent, or indifferent, but that everything from the smallest molecule to the largest star, exists for a time, contributes what it can, and then becomes part of something else. The Wolf-Rayet star in Gamma Velorum is doing exactly that, burning itself down to nothing, scattering its substance across the cosmos, building the future out of its own destruction. And somewhere, in some far corner of the galaxy, millions of years from now, a new world will form from the ashes of this star. Rain will fall on that world, carrying oxygen atoms that once burned inside WR11. Mountains will rise, threaded with iron from a core that collapsed in a fraction of a second. And if anything on that world ever becomes complex enough to wonder where it came from, the answer will be here, tonight, in the faint blue-white light of a dying star in the sails.